Hello, I'm Gonçalo Certo.
Hi, I'm Ricardo Campos.
Hello, my name is Pedro Peixoto.
Olá, I'm Pedro Santos.
We are the Portuguese team for IESO2022.
We are here at the top of Portuguese mainland, in Serra da Estrela.
Here to develop our Ntfi project.
Let us show you what we found.
All of us have certainly heard of climate change in one way or the other, as it is a literal hot topic these days. It's with no great surprise that it has managed to catch headlines in newspapers from all around the globe. After all, its nefarious effects have proven to be menacing many of the systems that contribute to the planet's stability. Yet, despite its global range of effects, climate changes are still surrounded by a lot of misinformation.
Before starting our approach on this topic though, we want to clarify a misconception that's often not addressed enough by the media: the difference between global warming and climate change, two different yet deeply connected terms.
While climate change refers to shifts in the average weather conditions over thousands of years, global warming is more often associated with the effects of human emissions to the atmosphere and their contribution to climate change since the beginning of the Industrial Revolution. With that out of the way, we can now continue.
By analyzing the gaseous contents from ice samples and oxygen isotope concentrations in microfossils from marine sediment samples, it's possible to extrapolate respectively ocean temperatures and gas concentrations in the atmosphere. From this data, we know that the Earth's climate has been naturally and periodically changing for millions of years, during the Quaternary and before, in what we call glacier-interglacial cycles.
This means that, although mankind is accountable for the current situation of runaway heating, that we'll explain later, climate change is a natural and cyclic process, and that's what we want to focus our investigation on: the natural changes in Earth's climate that occur and have occurred in the past, especially in the Quaternary, as a part of a well-synchronized system between the Earth, the Sun, and the Milky Way, and that marks those changes have lasted in our landscape.
The cyclicity of Earth's climate is due to three main phenomena of its orbit around the Sun. Eccentricity, the shape of the orbit, stretched by the influence of Jupiter and Saturn; obliquity, the angle between the Earth's axis of rotation and the normal to the plane of revolution; and precession, the wobble of the rotation axis around the normal to the plane of revolution due to tidal forces from the Sun and the Moon. The variations in these phenomena condition the amount of solar radiation hitting the atmosphere, thereby inducing long-term changes in the climate. All these variations are cyclic though, which means that events like ice ages and glacial periods are spread almost evenly throughout time.
Earth's localized phenomena like plate tectonics and consequent volcanic activity also contribute to changes in Earth's climate. Volcanic eruptions can release massive clouds of dust that block the sun's rays from reaching and heating up the planet's soil, resulting in periods characterized by lower temperatures, sometimes even worldwide.
Continental drift too plays a role in this phenomenon, as the moving land masses alter the distribution of oceans and sea currents, effect of this change in temperature flow in the planet. Mountains created by clashes between plates alter wind currents, also affecting the climate.
A big part of these changes is driven and propagated by feedback loops. This consists in cycles of effects that affect each other in some way. Focusing on glacial interglacial cycles, obliquity and albedo are currently considered the two main playing factors.
Albedo consists of the amount of incident radiation that's reflected back by a body. When Earth's obliquity is low, the hemispheres receive less radiation, allowing for snow to form. Being highly reflective, it boosts Earth's albedo and triggers a positive feedback loop. More reflected light allows for the formation of more snow, which in turn increases the albedo even more, creating less sunlight, more snow, more albedo, and so on.
When obliquity is high, the opposite happens. More light melts snow, so less albedo and even more light is absorbed. Together, the effects of obliquity and ice albedo feedback create and destroy ice sheets, regulating glacial and interglacial periods.
By looking at the landscape and considering these phenomena, we can discover the geological history of a certain place and understanding the processes it went through. In coastal areas, for example, the changing climatic factors alter sea level and thus cliff and coastal erosion, as well as sedimentary content in rivers and soils. A lot of this is recorded and preserved in rocks, making it possible to deduce ancient environments based on this data.
Mountainous terrains, however, form specific framings with unique temperature and humidity values, creating microclimates and unique ecosystems isolated from everything else. By analyzing the evolution of these ecosystems, we can understand the changes that occurred over time. These unique conditions also leave marks in geological substrate of the landscape, altering the rocks themselves or preserving evidence of ancient ecosystems. By then combining the information from both the biological and the geological standpoints, it's possible to reconstruct a somewhat accurate image of the past.
Currently, Earth is at an interglacial stage, having a natural increase in its average temperature while still maintaining some glaciers. Looking back at the Milankovitch cycles and other studies, the last glacial period, the Würm glaciation, started somewhere around 110,000 years ago and ended at about 11,000. We wanted to study the marks this period left in our landscape, so we went to one of the highest points in our country to find them, Serra da Estrela.
Serra da Estrela is located in the west half of the Iberian Peninsula and is part of the Iberian Central Cordillera, a mountain range encompassing geological formations from both Spain and Portugal, stretching for 115 kilometers and with an average width of around 25 kilometers. It stands out from the surrounding landscape, as its granite plateau abruptly pierces the metasediments, stabilizing afterwards in a northeast direction, towards the Meseta Central. It contains the highest point in mainland Portugal at 1993 meters.
Its formation goes back to the Neoproterozoic era, around 650 million years ago, when clay and sandy-like sediments were deposited in the Rheic and Paleotethid oceans, before the formation of Pangaea. The tectonic movements of the Variscan orogeny then compressed and forced the sediments up, creating schists and metagraywacks, among other metamorphic rocks. At the time, magma had been ascending, installing itself beneath the metasediments and forming granites.
Later, in the Cretaceous, further tectonic movements created the Iberian microplate. The ancient fault system was also reactivated, creating parallel slip faults, which with the help of tension reliefs ended up creating massive unattached blocks of crust. During the Middle and Upper Miocene, the faults began to behave as reverse, due to the compression forces between the African and Eurasiatic plates, lifting the crust blocks and creating the Central Cordillera. Differential erosion then carved the landscape, removing a substantial part of schists and graywacks and leaving behind the granites.
Serra da Estrela's topography and its proximity to the Atlantic Ocean make it a curious place from a climatological perspective. The main plateau bonds two main regions of temperate subclimates, CSB at northwest and CSA in the southeast. Both correspond to Mediterranean climates, being CSB cooler on average. This is because of air coming from the Atlantic encounters the mountains and is forced to go up, cooling in the process. It is then flushed down the Zézer and Alforfa valleys, creating a constant breeze across the region.
The air from the Atlantic is also very wet. However, after cooling, it loses the capability of holding that water, creating condensation and precipitation in the northwest side of the plateau. These two phenomena still allow for the existence of two quite different biotic communities in Serra da Estrela.
The populations also feel the effects of mountain in the weather. Phenomena like cold air drainage and mountain and valley breezes, as well as the natural topography of Estrela, create areas with smaller temperature changes and higher temperatures in general. These areas coincide mostly with valley slopes and, not surprisingly, with populated regions. The patches of relatively stable and warm weather allow for the plantation of crops and the establishment of villages like Manteigas. In the past, the winds from the Atlantic made the top parts of Estrela very cold and wet, allowing for the formation of snow. The plateau at the top allowed for huge amounts to accumulate in the winter. This snow would then survive the summer and increase its thickness over the years by the processes we explained before, compacting itself to form an ice sheet that achieved at one point a height of around 90 meters. Due to its weight, this ice sheet started moving down the several river valleys, carving them into typical U-shaped glacial valleys.
Through their path, the glaciers created structures typical of glacial erosion like cirques and umbilic, the French designation for a specific type of cirque, mainly differentiated due to its shape and lower altitude. Still in French literature, umbilics possess a specific promontory-like structure, the verrou, created as a glacier carved the umbilic. Other forms of glacial erosion in Estrela include moraines, hanging valleys, and nunataks.
Nunatak, an Inuit word for lonely mountain, is a portion of rock that was never covered by the ice. The motion of the glacier runs the under part of the nunatak but leaves the top untouched. Estrela has three main nunataks, called cantos: Cântaro Raso, Cântaro Magro, and Cântaro Gordo. Hanging valleys are just like normal glacial valleys, but they tend to be smaller and extend themselves over bigger and older glaciers. After the retreat of the glaciers, we are left with a valley that seems to be hanging over the other. An example of this is the Candeeira Hanging Valley. Moraines are simply the alignments of sediments left after the glacier's retreat.
These structures possess a huge transport energy, being able to move everything from small grains to house-sized boulders. The sediments themselves are called till or glacial till, and the bigger blocks are called erratics. In Estrela, near Lagoa Comprida, we found more evidence of glacial transport based on the recognition of these erratic blocks. We observed that some lithological features of certain granitic blocks, such as types of minerals and their size, differ from the ones in the substrate below. This led us to conclude that the blocks had been moved from their original place. The massive ice sheets are also able to scratch the rocks, or crush them, creating a polished effect that you can feel by touch.
As we've said, rocks often preserve remains of the past. In Estrela, researchers have looked into traces of trapped pollen to study the environment in Estrela during the last glacial period and have identified periods of lower temperatures and smaller amounts of vegetation. Oxygen isotope measures also match ice records around the world, supporting the hypothesis that glaciers did exist in Estrela during the Würm glaciation until around 14k years ago.
To find further evidence of glacial action on the landscape, we went to the field and collected samples. We studied till samples from a moraine, and as a source of comparison we got 4 other samples to study shape, size and appearance in order to explore glacial till features and deduce the agents involved in its formation.
We acquired sediment samples from a beach, a river, a desert, and from a granitic outcrop. This last sample was also collected in Estrela, right next to the source rock, having suffered virtually no erosion, so it was used as a control to understand the effects of weathering and consider them in our evaluation of till sediments. The study involved 2 main procedures, observation and sieving. We started by looking at the samples in the binocular loop, associating the known samples to their known formation processes. As an example, aeolian sediments tend to be small, very well calibrated and unpolished, as a result of constant collisions that break and scratch the sediments. On the other hand, marine sediments are very round and polished, given the constant flow of water around them.
After looking at the samples, we passed all the sediments through a set of sieves, in order to organize them in percentages of different sizes of grain. In this way, we created a granulometric curve for every type of sediment, plotting them for a comparison.
As we can see, the fluvial, marine and aeolian sediments are mainly spread across 3 categories: less than 177 micrometers, less than 297 micrometers, and less than 850 micrometers, which means they are well calibrated. The granitic and till sediments, however, have their mass somewhat equally distributed in all categories, meaning they are badly calibrated. Differences in calibration are due to the transporting agent's properties, so we looked more into that.
The transporting agent's energy determines the size of grains it can carry. High energy agents can carry all sorts of sediment size, leaving badly calibrated deposits. Wind, for example, doesn't have much energy, so it can only act significantly on the smaller grains, mostly by making them collide and leaving them highly scratched and unpolished. Sediments exposed to water, on the other hand, are typically polished and also well calibrated.
Our till sample is very badly calibrated and does not present any signs of wind or water action, resembling the appearance of the granitic sample, which did not suffer erosion. This indicates that the agent that transported the till had a high transport energy, while somehow not affecting the sediments themselves.
Being glaciers huge sheets of solid ice, they carry massive blocks of rock, fulfilling the high energy requirement. Also, while moving, the glaciers rip pieces of rock from the faces and the bottom of the valley, scratching them against the bedrock and creating the marks we've shown before. The ripped glacial sediments then remain in the glacier, not having any interaction with the external agents or other sediments whilst in there, thereby explaining the resemblance with the non-eroded granitic sediments. The results thus support the idea of glacier erosion for the till.
Having completed our study on natural causes for climate change at the Marci lab from Portugal during the Würm glaciation, we turn to the most recent changes, mainly caused by humans. Since the beginning of the Industrial Revolution, we've increased the amount of CO2 in the atmosphere by 48%, greatly contributing to the greenhouse effect.
This effect occurs when substances like CO2 and CH4 are present in the atmosphere. Radiation from the sun gets reflected and trapped, increasing air temperatures. In the past, this blanket-type effect was responsible for providing the ideal conditions for life to thrive. However, the excessive accumulation of greenhouse gases due to an overconsumption of fossil fuels and deforestation is causing an atypical increase in the planet's average temperature, beyond the values expected by naturally caused variations. As we've said before, this phenomenon is called global warming.
Human-induced climate change is causing adverse impacts both to nature and people, and is currently mainly expressed in more frequent and intense extreme weather events. Impacts to ecosystems, people and settlements have resulted from observed increases in the frequency of these events, including hot extremes both on land and in the ocean, heavy precipitation, droughts and fires. Besides that, approximately half of the species assessed globally have shifted polarwards, or on land, also to higher elevations due to increasing temperatures. Global warming already altered terrestrial and aquatic ecosystems worldwide, with multiple impacts evident at regional and local scales. In addition, climate change also has adverse impacts on human life, affecting water security, food productions, infrastructures, and even physical and mental health. The economic impacts derived from all of these situations are also quite significant, increasing the already delicate humanitarian crisis.
Patterns of unfair economic development, unsustainable ocean and land use, ongoing colonialism and corrupt governance are responsible for approximately 3.4 billion people living in contexts of high vulnerability to climate change. This whole situation, as well as all the consequences we observed and have predicted, do make us think about our environmentally irresponsible behavior and how we can fix the situation we have created. So, what are the solutions?
Humans could adapt, as we always did. However, our incautious activity creates unpredictable results that will need outrageous amount of resources to counteract at an official level. So, as a way to at least delay this situation, it is fundamental to develop and use resources which respect our planet's natural behavior. Implementing reliable energy sources with an efficiency similar to fossil fuels is a big challenge for mankind, yet a vital step towards mitigating our impact on the environment and assuring our survival.
To learn more about sustainability and the processes of energy production and management, we visited 3 facilities in Serra da Estrela, which exploit 3 different resources: geothermal energy, hydric energy, and pegmatites containing lithium minerals.
Hydric energy is currently the most used form of sustainable energy, accounting for 70% of the total energy worldwide, only behind coal and natural gas. In Portugal, over 50 hydroelectric facilities are responsible for more than a fifth of the total energy production. The Desterro hydropower plant was one of the first hydroelectric power plants to have been installed in Portugal and the first in Serra da Estrela.
Originally built in 1909, it was later replaced and turned into a museum, where we got to see some of the old engines and how the system used to work. The replacement now belongs to a chain of 5 hydroelectric plants located along the Alva River that capture the energy from the water coming down the mountain through massive pipes, to then return to the same river. After a great conversation with one of the engineers in charge of the plant, we came to know that the plant only converts the kinetic energy from the huge masses of flowing water, while keeping strict control on the machines so they don't leak any oil into the water. This means that it comes out as clean as it enters the facility, posing no risk for the environment whatsoever.
The total array produces around 240 gigawatts of energy yearly, with the capacity of powering more than 100,000 homes in the region.
Still in Estrela, in the municipality of Manteigas, we saw how geothermal energy is used by local touristic establishments to heat the water for their pools. At a depth of around 100 meters, a captive aquifer holds the following water under pressure, which allows for a simple extraction without the need of using a pump whenever the site is located below the phreatic level. The Villarissa-Manteigas fault, located in the same area, is responsible for heating the water in the aquifer to temperatures above what would be expected. After doing some measurements, we found out the water comes at around 40 Celsius degrees. Even though these temperatures do not allow for a direct energy production, like in Iceland or Azores, it is still more than sufficient to create a natural heating for pools and hotels, replacing gas as an energy source, and thereby reducing the carbon footprint on the environment.
Lastly, we visited Seixo Amarelo, a pegmatite mine and Felmicas transformation plant. Pegmatites are igneous rocks with very developed crystals that are formed in the last stages of magma's crystallization. The final residual magma is rich in elements like alkalis, fluorine and phosphorus that end up trapped in these final formations with granite-like composition and are often associated together. In Seixo Amarelo, these pegmatites are extracted to form a powder that will be the main component in some ceramic products. These rocks have relatively large amounts of minerals like lepidolite, spodumene and petalite, which contain lithium. This element, when a part of ceramic mixtures, lowers its fusion point, allowing for better handling while also hardening and whitening the final product.
While talking to the mine engineer, we got to know the environmental policies of the company. Since only the pegmatites are extracted, the remaining material, which is mostly granite, is left on site. After the resource is depleted, the mine is covered and several reforestation measures are in place to reestablish the environment to its original state.
In the transformation plant, we observed that almost all the pegmatite material is converted to some sort of product, with only the finest powders as a waste. The use of lithium minerals to lower melting points also benefits the environment, as less fuel is used to heat the mixtures, saving on emissions. But what exactly is lithium? Well, lithium is the third element of the periodic table, belonging to the alkali group. In nature, it appears alongside other elements in minerals like petalite, lepidolite and spodumene, with its concentration differing from one mineral to another. This element is also found in subsurface brines, which are currently its main source, at around half of total global production.
In our electricity-driven world, the need division lithium in energy storage has made the market quotation for this element rise up so much that it seems vital to find new deposits of lithium. The eventual depletion of brines will leave pegmatites as the most reliable source. This is where Portugal could take a role, as it has the biggest lithiferous pegmatite reserves in Europe and some of the biggest in the world, possibly making Seixo Amarelo a viable lithium-only mine. Yet, despite its potential, Portugal only extracts lithium for the ceramic industry. While talking to the production manager, she ensured that for now, lithium is only a secondary product which benefits the final materials. With this element being such a crucial part of their ceramics, she confirmed that a full transition to something like a battery lithium mining would destroy the business.
With this visit, we concluded that despite the massive lithioniferous potential of Portugal, lithium is already incorporated in current industry and economics, and despite posing no additional harm to the environment, if the right measurements are taken, overexploitation could still lead to the failure of other economies. Thus, any decision regarding the topic would have to be extremely well considered.
During this journey, we found the whole area of our country in a completely new way. We traveled through space and time to discover the wonders of our planet's past history, reading what others wrote and going to the field to experience by ourselves. With the help of our mentors and all the ones who kindly taught us all they knew, we were able to understand this topic, at least enough to compile it all in a video to show you. We hope you've learned something, but maybe more importantly, we hope you enjoyed it. To all of you, the best regards from Portugal. And don't forget, keep on rocking!